Welcome back to module 8 where we are discussing light atom interaction. So far we have given the classical description of light using Maxwell's equations, and we have seen that Maxwell's equations are formulated based on electric and magnetic field. So in a medium, if the light is propagating through the medium, then I have to check what is the characteristic of electric and magnetic fields I have in the medium. Based on that characteristics, I can explain the nature of light, classical nature of light. But the problem is that in time-dependent Schrodinger equation, which will ultimately will use time-dependent Schrodinger equation to understand light atom interaction. In TDSE, we use potential term, we use potential form, and that's why what we need to do is that the field formulation needs to be converted to potential formulation to get the right form, which is which we can include in the time-dependent Schrodinger equation. So we will see how to get that potential formulation of Maxwell's equations. We have used 4 equations based on electric and magnetic fields. All 4 equations will be combined together in the potential formulation, and then we can use that potential formulation for the TDSE. So we'll spend little time on this formulation. In the following formulation, we'll make use of rigorous vector algebra to obtain the potential formulation of Maxwell's equations. Now, we already have seen that one of the equations of Maxwell's equations in vacuum. So we are basically working in vacuum. In the vacuum, so medium is the vacuum, which is the empty space, and we are assuming that the light is propagating through the vacuum, and when the light is propagating through the vacuum in the medium, different points we can check what is the nature of E and E fields and H fields, and we know that in the vacuum this is going to be divergence-less. That's the characteristics we proposed, revealed by Maxwell's equation. This is going to be always 0. The dot product would be 0. Mathematically, it is the dot product with the del operator, and physically it means that the divergence would be 0. And because the divergence is 0, one can also write down in the medium, even in the vacuum medium, we should represent this magnetic field more appropriately in terms of B. That is called, the name is given as magnetic induction. Magnetic induction, which is nothing but mu naught H. That's the another more appropriate way of presenting the magnetic field in the medium. We do not want to get into the more details of this derivation, because this comprises entire classical description, physical optics part of, and we don't want to get into that. So in vacuum, this is we will present it in terms of B. So in terms of B, even the entire equation remains to be the same. The magnetic induction, technically it is called magnetic induction, but we can also say that it's a magnetic field in the vacuum. So magnetic field remains divergence-less in the vacuum. So B remains divergence-less. And if B is divergence-less, then mathematically one can propose that B is a curl of a vector. And why, I will prove that. So if because B remains divergenceless, then one can write down B is nothing but curl of a vector. That's the way one can represent. And why it should be, what is the basic reasoning behind this is because because divergence, this is a very frequently used vector identity. I told you that we are going to use vector algebra rigorously here. So one of the vector identity is that divergence of a curl is 0, and that's exactly happening. So if B is represented as a curl of something, curl of a vector, curl of a something, let's say A is something so far, let's say, then its divergence is going to be 0. So it is just a mathematical consequence, and we will begin with this pure mathematical idea and try to understand the physical meaning later. So one can prove this. If B is represented as a curl of A, then its divergence is going to be 0, and one can prove it like this way. This is nothing but A, that's the way we are representing, and if it is so, then I can represent it like this way. Curl is represented by, I have shown curl is represented by this. And then AX, AY, AZ. So what is going on, this AX, AY, AZ are the components of the vector along the x, y and z directions respectively. So this vector we have considered, and what is the meaning of this vector will come later. But right now we are just saying that if B is a curl of a vector, then immediately this relation holds. So that will be satisfied immediately, and that's the reason why we have written this B as a curl of vector A. And AX, AY, AZ, it's just if A is the vector, then in 3 dimension one can represent its components. Components is going to be X, Y, Z components. So this component is going to be AX, this component would be AY, and this component would be AZ. Those are the components we have written. Now if I explicitly do this, then this is a del operator, so I will write down its explicit form of the del operator. It's a vector differential operator, and then it's going to be dot product with this one, and this determinant can be written in a following way. This is I multiplied by del AZ del Y minus del AY del Z plus other 2 terms will be there. But one thing we see that this dot product will exist only when we take the derivative. This part this is associated with the I vector, this unit vector, and this is associated with the unit vector. So only this term will exist. Other terms will not exist, because dot product doesn't give you the dot product becomes 0, such as I dot j, it will be 0. So other dot products will be 0. So only dot product which will exist is the which is containing the same unit vector. So it is nothing but this is z y minus ay az. So what we see here, and plus other 2 terms, there are 2 terms will be there. Now what we see that this is with respect to x, this is the derivative with respect to x, but these terms doesn't have any x dependency. So this entire term will be 0. Similarly, other terms will be 0 also. Other two terms will be also 0. So entire analysis shows that that if I have if I can represent this B as a curl of a vector A, then its divergence would be 0. Then only its divergence will be 0. So this is proved. So this is mathematically correct. Mathematically correct. But physically, what does it mean? We will come back. And remember, this physical meaning of this part, this particular, and this A will be called vector potential. This is the first time we are introducing this vector potential. So far we have shown its origin, mathematical origin, in terms of the vector. What is its mathematical origin? It comes from the fact that because B has to be divergence-less, then B can be expressed in terms of a curl of A. So it is mathematically correct, and this A is called vector potential, which is representing the magnetic field. So the potential associated with the magnetic field is actually vector potential. And at this point, we can assume that A is just a mathematical function whose curl is B. So A, what is A? A is a mathematical function, vectorial function definitely. A is a vectorial mathematical function whose curl is B. So it's representing B basically in terms of this this curl notation. But later we'll find out that this has many significance actually, this vector potential. Vector potential has many significance. So one can imagine it is something like this. B is a magnetic field, and field is nothing but a force, and force originates from certain potential. In this case, force, this magnetic force is originating from vector potential. That's the way one can imagine. But there are many other significance of A, and one of the challenging part of physical optics is that to give a pictorial view of vector potential. Vector potential, the concept, to understand the concept behind vector potential, it takes long time. For somebody who is not familiar with this, with the electromagnetism. But we will try to give some pictorial meaning of vector potential. One of the physical significance of representing B in terms of vector potential is that for a charged particle, if I have a charged particle, plus Q charge particle with mass m, and velocity, let's say v, if this particle is interacting with electromagnetic field, if it is interacting with electromagnetic field, with electromagnetic field, then the inertial momentum is going to be definitely mv, but this we know that mv is the momentum is conserved in classical mechanics, and momentum is conserved. But when a particle, charged particle, is interacting with electromagnetic field, then its inertial momentum is not conserved. Its generalized momentum is conserved. That's called canonical momentum, and canonical momentum is expressed by this mv plus qa. This entire thing is called this p canonical. This is conserved. So this is called canonical momentum. This is something which I am introducing, and these concepts are taken from electromagnetism, the classical theory of charge particle interaction with electromagnetic field. And we are just picking up the useful information which will be used in the context of light atom interaction. So just one thing we should remember, that when a charged particle is present and interacting with electromagnetic field, its inertial momentum is not conserved. Its canonical momentum, total canonical momentum or generalized momentum is conserved. So this is conserved, and that can be proved. We are not going through. We are not going to show the proof for this, but what is interesting to note, that this QA term needs to be added to the inertial momentum mv to fulfill the momentum conservation law of a charged particle in the electromagnetic field. So A has a big significance. This potential, vector potential, comes into the momentum conservation law. It is more like when I do not have electromagnetic field, a neutral particle is moving, then we say that its kinetic energy plus potential energy part, total energy is conserved, something like that. So under conservative force field, we say that the kind of potential energy part has to be added to the kinetic energy part, then total energy is conserved. That's the way we say. Similar, in a similar sense, when a charged particle interacting with electromagnetic radiation. Remember, electromagnetic field, in order to interact with electromagnetic field, the particle has to be charged. If the particle doesn't have a charge, then it cannot interact with the electromagnetic field. And I mentioned before that when a charged particle is not moving, it is static, standing at a single point, it's not moving with a velocity, so velocity is 0, then electric field can act on it, but magnetic field cannot act on it. In order to have some action from magnetic field, or in order for the charged particle to experience magnetic field, it has to move, it has to have some velocity. So these are the different consequences we are picking up randomly, but knowing the fact that they are useful in the context of light atom interactions, but we are actually picking up those useful information, those information which will be useful for the present discussion of light atom interaction. So we'll move on. So we see that vector potential has a big role in the light atom interactions, but its origin was pure mathematical. Because it is divergenceless, one can immediately express as a curl of this function, and this function is called the vector potential. Now, if we have that, then one can actually insert. So previously we had this equation, this curl equation. We said that when a medium, through a medium, when the light is propagating through the medium, because it is vacuum, in vacuum we are looking at it. So we have this electric field and magnetic field, and we have to check the nature of the electric and magnetic field in the vacuum. And we have seen that although they are divergenceless, but their curl exists, and this is the way we got another equation, Maxwell's equation. So we can also write down this as B dt, because B, we have defined B is nothing but mu naught H. It's another physical quantity which is describing technically better way of presenting the magnetic field in terms of B. That's all. I mean, that's the way we can think of it right now.